Here we are in section 5-4, exercises 25 through 30. Number 25, we're factoring like crazy. You'll notice we have 1, 2, 3, 4 terms, but before you go to grouping, notice we've got to do that greatest common factor. You'll get much smaller numbers and it'll be better for you. Take out anything you possibly can here, which is there a 10? Nope, just a 5. 5 comes out of there and we're left with 8. A squared b minus 4ab plus 8a plus 3. Now we have 1, 2, 3, 4 terms. So we would slice this in half to see if grouping works, and we'd take out a 4ab. And we'd be left with, let's do that different color cool thing. We'd be left with just an a. Is that right? No, 2a. Yeah, if 8 divided by 4 is 2, a squared divided by a is just a, and then b minus 1. And can you take anything out of there? Nope. So you would be left with just a plus like a 1 and 8a plus 3. You are stuck. These two blue things do not match, so you can't take them out. So let's go backwards on that and leave it with as much factored as we could. That is your answer. Alrighty. Number 26, 25x squared plus 14x plus 36. Greatest common factor. It's got 5s, 2 and a 7. Nope, nothing common. How many terms? 3. Leading coefficient? Not equal to 1, so let's check. Ooh, this is a perfect square. Let's check and see if it's 5x plus square root of that 6. Does it work? 5x squared is there, yes. 5 times 6 is 30. Doubled is 60. No, it is not that one. Shoot, so we actually have to do the real thing. 25 times 36. That didn't work, so we're now down here at the AC method. 25 times 36 is 900. Is that correct? Yeah, it is. So that's 1 and 900. 2 and 450. 3, does 3 go into that? Yeah, 3 goes into it 300 times. 4 goes into it 225 times. 5 goes into it 180 times. 6 goes into it 150 times. 7, no. 8, no. 9, yeah, 9 goes into that 100 times. 10 certainly goes into that 90 times. 11, no. 12. Now notice here, it's starting to get a little tough. You can do this by your calculator, or you can see, oh, if I double 6 to 12, then I could half 150 to 75. It'll be 12 times 75. That's pretty cool. 13, no. 14, no. 15. Yeah, if we times this by 3, we could divide this by 3, which is 60. 15 times 60 is 900. 17, 18. Yeah, if we double 9, we get 18. If we half that, we're at 50. Wow. 19, 20. Yep, 20 is 45. Holy cow. Now we'll notice that as we add these, they're both positive, and we add them, you can kind of see that 901, 452, 303, 226, they're going down further and further. At the end of this row, we're going to hit 30 times 30. That's the square roots, and that adds to 60. Everything else will be above 60 when they add together, which means this guy is not going to happen. Once it wasn't the square, we could have checked the 30-30. It's the smallest number that can be in the middle when you have two perfect squares. Interesting. Long lesson to learn there. We could do, let me see, 25 and 36, and then that's the last one. That's all that goes into it. So this one is, after all that work, no, it is not possible. Wow, but that's how you can tell for sure, because none of these would add together to give you a 14 in the middle, so it is impossible to break that apart and factor it. Wow. Number 27. Greatest common factor? Nope. 3 terms, leading coefficient equals to 1, so this is going to be b something and b something. What times is to a positive 16? and adds to -8. Well, I don't know. Let's look. We got 1 and 16, 2 and 8, 4 and 4. Oh, if these are negatives, oh, silly me. Look at this. 1 is a perfect square and 16 is a perfect square. We could have done b minus 4 squared and just double check that 4 times b times 2 is indeed -8. Yeah, it would have worked. Doggone. But yes, that's how it factors, and you could do it either way. Number 28. Negative x squared plus 4. Oh, I don't like that negative in front. You could write this, take a -1 out, and then you have x squared minus 4, which in two terms is a difference of perfect squares. So you could write it like this, x minus 2, x plus 2. That would work. I want to just show you that this other problem could have been written this way. And it's still a difference of two squares, but now it has 2 minus x, 2 plus x, which is just a little bit different. This looks a little bit different where we don't have the x's first, and it's not as conventional. It's not as usual to do it, but it's certainly correct. Notice that if you took this -1 and jumped it in here, you'd have a negative x plus 2, or a 2 minus x, which would be the same as this. So they are both technically correct. All right, next one. Number 29. Any greatest common factor? Nope, no greatest common factor. 1, 2, 3 terms. The leading coefficient is a 1, so this is a quick guy. M here, and a -12 out here. 1 and 12, 2 and 6, 3 and 4. Some of you may be seeing it without this list. To me, it's very helpful, especially with minuses, to know that, ooh, what I thought was going to be a -4 and a 3, nope, it doesn't work. It's this guy right here, 2 minus 6. So that's a +2 and a -6. Correct. Excellent. All right, number 30, the final one. Ooh. This is kind of big. Let's see, is there a greatest common factor? I'm seeing 9s and 4s and 9s and 4s, so something's up. But there isn't a greatest common factor that we can do that with. So we're out here at 4 terms. So let's chop that guy up and see what we can pull out. We can pull out an x cubed, it looks like, is in both of them. And we're left with 9x squared minus 4. All right, now on this one, we're going to pull out a minus, and if we want to make it really explicit, put a 1 there. There's nothing really other than a 1 that can go into the 9x squared and the 4, but you'll notice that, yeah, we get a 9x squared. When we pull the -1 out of a +4, divide that, and we get a -4. Oh, so look at that. We actually have a 9x squared minus 4. And the other thing that's left is x cubed minus 1. Well, that looks all fine and good, but notice the things that are left. This is a difference of 9 and 4 are perfect squares. This one is a difference. This is a perfect cube, and that, number 1, is a perfect cube. So we've got a difference of squares and a difference of cubes that we've got to deal with. So this guy right here, a difference of squares, we've got to take the square root, and we get 3x. Let's keep the colors, though, right? That we've done. This is 3x and a 2 and 3x and a 2. So that's one's a plus and one's a minus. So that one's finally broken down as far as it can go. Now the other one is a difference of cubes. So this is x cubed and this is 1 cubed. So we actually need to have x minus 1, and then what's the rest of that? It's huge. X times x squared will give us the x cubed. 1 times 1 will give us the 1, and the guy in the middle, the magic maker in the middle, is opposite sign plus 1x. And you will be tempted every time you do a difference of cubes, you'll be tempted to look at this and say, hey, can that guy go down anymore? Well, in order to do that, it would be a leading coefficient 1. And you would say, okay, what times's to 1 and adds to 1, and it is not possible. And it turns out that every time you do a difference or sum of cubes, this guy right here is not a quadratic that will factor down. So yeah, that was huge. Look at that. 1, 2, 3, 4 different terms. I mean, factors going on down here at the bottom of that one.